Hi, how's it going? This is my second video of integration with hyperbolic functions. If you're not watching my first video, then just give that one a go first of all, because I remind you about several important integration techniques that I picked up earlier in the year. This is my second video, and I'm just going to get straight into the examples. Right, first two are these. Okay. Now, before you go ahead and do them, just think about how you'd integrate it using trigonometry, as in similar terms, but using trigonometry instead. So how would you integrate sine to the power of 5x cos x? If you can't remember that, then you don't know your standard course well enough, is basically what I'm saying, okay? You need to know the standard course 100% before you can actually do the higher level course. So you need to know A-level maths before you can do further maths, okay? But also I'm hoping that going through some of this stuff will be good revision for the standard course anyway, because this is something that's come up before and it's fairly common. The idea is that you look at sine to the power of 5x and think about your answer being a power of sine x, and because we're integrating, we normally increase the power by 1. So you normally think about having sine to the power of 6x as your answer. Now, with integration, a lot of the time the method is to think about what the answer could be, try it out by differentiating, and then modifying your answer. Okay, sometimes it'd be completely wrong, but that's fine, because at least it tells you what direction you should not go in. And believe me, a lot of the time with integration, knowing what not to do is just as important as knowing what to do. Okay, because you need to get in the right path. In terms of your examinations, for example, the method marks are picked up by doing the right method. If you're doing the wrong method, if you're on the wrong path, you get 0 method marks. Okay, so it's quite important knowing what to do as well as what not to do. All right. So we're going to try this and see what happens. So if you try this, if you differentiate it, you've got 6 sine to the 5x, and then differentiate sine x, you've got cos x, okay? Which is kind of almost our answer. Yeah. So all I'm going to do is just put in a 6 there and a plus c, and then it'll be correct. Okay. I'm hoping you pick that up quite quickly and quite easily. All right. This one here, this is a similar thing, because what we're looking for is we've got one term there has got a multiple power, like power of 5 or power of 6 or power of n, say, and the other term is just a single power, like tang x or cos x. Okay. So let's consider our answer being a multiple power of sec x. Okay. So let's begin with y equals sec x to begin with, and consider the derivative of that. Now remember, because it's a reciprocal term, it's going to be negative when you differentiate it. So negative sec x tang x, and you can see that's where the tang x comes from. Okay, so having some power of sec x is going to be our answer. Let's just suppose it's sec squared x. So what do we get when we differentiate that? We'll bring the 2 in front, so you'd have negative 2 sec, and then decrease the power by 1, negative 2 sec x, then differentiate sec x, you get sec x tang x. So simplifying, that would be negative 2 sec squared x tang x. Did you not follow that? Well, let me just do another one for you. Let's just suppose it is sec to the power of 3x. So now when we differentiate, we'll have a 3 there. So negative 3 sec, decrease the power by 1, it will be sec squared x. Then differentiate sec x, you get sec x tang x. So it will be sec cubed x. So you can see the pattern there is that the power is always going to be the same when you end up differentiating it. Okay. So that means we're going to try negative sec to the power of 6x, and I'm going to leave a gap there for the coefficient. Okay. So when we differentiate sec to the 6x, okay, you're going to have 6 sec x to the power of 5, so sec to 5x, and then sec x tang x, sec to the power of 6x. Okay. By the way, yeah, I might have missed out saying the odd negative or 2 in that, but yeah, the negative symbol is there. It's, yeah, okay. The important thing is the actual, yeah, you know what I mean. I'm just going to put in a 1/6 there to make it correct, okay? Because then the 6 times negative 1/6, that gives the negative 1, and then the negative becomes positive when you differentiate, and so on. Okay. Those are the sorts of integral results that you need to remember. Okay, and it looks something like this. Let me give you a slightly different one. Okay, so let's suppose we had cos to the power of nx sine x. as I said already, what you're looking for is you've got one term there, either trigonometric or hyperbolic, okay, and it's a multiple power of n, okay, where n is not 1, or there's a simple case, and then the derivative of that, cos x, is there, okay, or a multiple of that is there, okay. Pause the video maybe, have a go at it. This is the general result then, so you're going to end up with cos to the power of n plus 1 x, yeah, and consider what you get when you differentiate that. The n plus 1 will go in front, won't it? So you need 1 over n plus 1 there. And then you decrease the power by 1, so you get cos to the nx, differentiate the cos x, and you get sin x, okay? So treat that as a generalisation, a general result of integrating cos to the nx, sin x. And I'm sure you could write down a generalisation for sin to nx, cos x, or a generalisation for sec to the nx, tan x. Maybe do that as extra. Maybe just pause the video and do it as extra before moving on, just to make sure you've fully got the hang of those particular integration techniques. Okay. Okay, these ones, they're fairly similar in terms of their technique. Can you see why they're similar? It's because they're both natural logarithms. Your answers will be natural logarithms. Why is that? Well, this one here, hopefully you remember from integrating tan x, the method is just to rewrite it first of all, isn't it? You write it as sin x over cos x. So tan x, you write as sin x over cos x dx, okay? And then you can see that's obviously a natural logarithm, isn't it? Because it's your classic case of differentiate the denominator, you get the numerator exactly, all right? So this would be natural log of cos x. Now, you might wonder about the modulus brackets I've inserted there. I'm going to ask you a question. Do you actually need the mod brackets in this case? The answer is no. Do you remember what the graph of cos x looks like? If you're struggling with that, then you're really not on top of it. Okay, you need to know what the graphs of at least sin x and cos x looks like without actually looking it up. Okay, you need to know it from memory. Okay, so cos x, remember that's the catenary, isn't it? So if you want, it kind of looks like a parabola, but it's not. But it's a catenary, okay, passing through 0, 1, so that's cos x, okay. So I've not labelled the axes, I really ought to, shouldn't I? And then sin x, what does that one look like? That kind of looks like a cube graph, okay, but it's not a cubic graph. I keep saying this, okay, but to try and remember the cos x, the catenary, okay, looks like a quadratic x squared graph. The sin graph looks like a cubic graph, okay, you just kind of need to know those. Anyway, the point I'll make here is that cos x is always positive, so you don't actually need the modulus brackets really. However, you're not going to get marked down an exam just by inserting modulus brackets when they're not needed, okay. My advice is, if you're not sure, just put them in. Usually when you're integrating, you've got a natural log, normally you put the modulus brackets in, okay, but just be aware when you can do. So another example, okay, I might have gone through this one before. Natural log of 1 plus x squared. You don't need modulus brackets around that, do you really? Because when you put in any real number, you're going to get a positive result, okay? But you'll just notice that I put in the modulus brackets just out of habit, and you're not going to lose any marks for it, okay? Right, this one here, have you worked out why that's a natural logarithm? It's because when you differentiate the denominator, this is what you do to check, of course. This is one of your many in your armoury for, what do I want to say? Your integration techniques is what I'm saying. This is one of your tools that you have in your massive box. Think about having a garage somewhere, like the one I'm in now, okay? And you've got toolboxes everywhere, okay? In each toolbox, you've got a technique for integration, okay? This is just one of many techniques that you need to have, okay, in your toolbox, okay? Checking when you differentiate the denominator, do you get a product of that on the denominator, okay? Yes, you do, because when you differentiate tan x, you get sec squared x, which is on the top, okay? So that tells us our answer is going to be the natural log of, here come the mod brackets again, 2 plus 5 tan x, okay, let's put in the plus c as well. Let's just check, so we differentiate that, so you get 1 over 2 plus 5 tan x times by the derivative of this, which is 5 sec squared x. There's no 5 there, so we'll just put in 1/5 at the beginning, okay. Right, next are two very common standard integral techniques that you need to be able to, or just know off the top of your head basically, okay? That is the integral of sin squared x and cos squared x. And again, I'll just throw you back to trigonometry. If you can't remember how to integrate sine squared x and cos squared x, then yeah, you need to go back and look at it basically. Okay, you need to know what to do. Okay, you need to look at the appropriate identities. So I've written them down for you. Okay, as a reminder. So in hyperbolic identities, you've got cos 2x is cos squared x plus sine squared x, which is the same as 2 cos squared x minus 1, which is also the same as 1 plus 2 sine squared x. You just need to know which ones of those you're going to use for each case. Okay, so obviously for this one, you'll use this one. Okay, so you've got to rearrange that. Okay, I know there are identities, but I'm just quite equals there. Okay, this integral is the same as this integral here. Rearrange that, so you can have cos 2x minus 1 all over 2. Okay, so you'll have 1/2, and what did I say? Cos 2x minus 1. Cos 2x minus 1 dx. Alright, and that's your standard technique. Okay, your standard result for doing that. So when you integrate half cos 2x, you're going to get 1/4 sine 2x, and then you integrate negative half, you get negative half x, and then plus c. So that's that one done. For this one, you're going to use that one there, aren't you? Okay, so cos 2x is 2 cos squared x minus 1. So when we make cos squared x the subject, we're going to have cos 2x plus 1 all over 2. So 1/2 of, what did I say, cos 2x plus 1, cos 2x plus 1 dx. Okay, and then we integrate this. Right, notice how they look remarkably similar, okay, in terms of your answers. So you have 1/4 sine 2x plus half x plus c. Okay, please commit them to memory. Okay, just know the actual techniques for doing those. These are very simple questions. Okay, you can't afford to be stuck on the basics like these. Okay, next example coming up. Alright, so I've just taken you through the questions where you have to integrate sine squared x and cos squared x. The next obvious one then is tan squared x. Well, it's not one of those identities, is it? So let's just put that away. It's the identity involving tan squared and sec squared, isn't it? Now, if you can't remember what the identity is, just think about sine squared x and cos squared x. So it's cos squared x minus sine squared x is 1, is the identity, yeah? And just divide both sides by cos squared x. So you get 1 minus tan squared x is equal to sec squared x. Okay? Like you would if you try to remember the identity involving sec squared x and tan squared x. You start off with sine squared x plus cos squared x equals 1, then divide both sides by cos squared x, wouldn't you? So we're just going to rearrange that first of all. So let's just do that. So it's the same as 1 minus sec squared x. Okay, like that. And then we can integrate. So integral of 1 will be x. And then remember, when you differentiate tan x, you get sec squared x. So subtract tan x and then plus c. Okay. Okay. When it comes to integrating single terms like sine x raised to a power greater than 2, it becomes harder. Okay. So I've taken through sine squared x, and you can see what to do with that. But when it comes to sine cubed x, sine to the 4x, sine to the 5x, it does actually start to become much harder. In fact, for higher powers, we use a different technique altogether, which will be coming up in another video later on. All right. But for sine cubed x, because the power is still relatively low, power of 3, we can still do it reasonably well using some hyperbolic identities. Okay. What we're going to do is just rewrite it as sine squared x, sine x. Okay, just like that. And we use an identity for sine squared x. Remember the identity for sine squared x? It's just right up here. So you've got cos squared x minus sine squared x is equal to 1. And so sine squared x is going to be cos squared x minus 1. Okay, so integral of cos squared x minus 1 sine x. dx, and then let's just expand the brackets there. So we'll have the integral of cosh squared x sine x, subtract sine x, all in brackets there, dx. Okay. Now, I've shown you already what to do with an integral like this. Okay, I even talked about a general result in terms of cosh to the power of nx sine x. So maybe you can just write that down straight away. Can you? Pause the video maybe, just have a think about it before I write it down. Yep, it's going to be something to do with cosh cubed x, isn't it? Because remember I talked about this case where you just have 3 cosh squared x and then sine x. So because there's no 3 there, I'm going to put it in 1/3. And then this one here is kind of obvious. So it's going to be subtract cosh x and then plus c. Okay. Now notice, because I needed a bit more working for that one, I've started to write my answer down the page. Okay. It's quite, well, to be honest, at this stage in your mathematical learning, I shouldn't be telling you, should I, about writing down the page. You should just be doing it. Are you still writing across the page? What's the matter with you? What's the matter with you? Write down the page. That's what mathematicians generally do. Okay. Now here's a different sort of looking integral, isn't there? Integral of e to the 2x sine x. Okay. Now I'm just going to remind you about how hyperbolic functions can be written in terms of exponentials. And here's a tip for you. When you see an exponential inside an integral like this, generally it's a good idea to try out writing that in exponential form to see what happens. Okay, so we're going to give that a go. Right, so you'll have e to the 2x. And then remember, when you write it in hyperbolic form, it'll be half. Let's put the half outside the integral bracket, shall we? So half there. And then you have e to the x subtract e to the negative x, okay, dx. Now that's looking like a pretty straightforward integral, isn't it? Well, it should be. Okay. So this is one of the things I love about integration. You start off with something that looks quite difficult, and with the right technique, it becomes so much easier. Okay. It is great. I still love that sort of thing. Let's expand these brackets. So you'll have e to the power of 3x, then subtract e to the x. Okay, so that's looking quite lovely and easy, isn't it? Okay. So integral of that is going to be 1/3 e to the 3x times by half, of course. So 1/6 e to the 3x, and then subtract a half e to the x plus c. Yeah, wasn't that nice and straightforward? Okay. Right, I'll look at this question again, but this time let's consider using integration by parts. Because let's be honest, as soon as you saw the integral, that might have been something you're thinking of. And, you know, fair play to you. A standard integral technique that you'll have learnt already is maybe how to integrate e to the x sine x, in which case you have to do it by parts, because obviously we don't have the luxury of being able to write sine x in terms of exponentials like we could with the sine x. Okay, so you'd have to do that by parts. Okay, so what's an interesting thing to do is consider how we'd integrate this by parts. So we're going to give this a go. All right, so the method is you can let u equal one of those terms and dvdx is going to be the other. Now purely because it's in that same order, I'm going to write u equals e to the 2x, and then du dx will be 2e to the 2x, and then dv dx will be the other one, sine x, in which case the integral of that is going to be cosh x. Okay, and then we just substitute into the by parts formula. Now, this integral here I'm going to call I, so the integral is going to be uv, so e to the 2x cosh x, subtract the integral of v du dx, so 2e to the 2x cosh x dx. Okay. Now already you should be thinking this is actually a bit longer, isn't it, than the first method. Okay, yes, it is longer, which is why turning this into exponentials is the best way to go. But let's just see how we, because sometimes the good thing about mathematics is seeing what other methods are available to us. Okay, so we got to this stage, so part of our answer, our final answer will be e to the 2x cosh x. We just got to figure out this integral here. So what I'm going to do is use by parts again on this. Just to make it easier, what I'm going to do is I'm going to just write the 2 in front of that, because then in terms of the u, I can do the same again, let u equal e to the 2x, and u dx is 2e to the 2x. Only I need to change this, don't I? Yeah, I need to change that around. So my dv dx this time will be cosh x, and then v will be sine x. All right? And let's just go and substitute. So subtract uv, so I'll tell you what, let's just use the brackets so that we don't get confused, okay? So 2, and then open brackets. So uv, which is that times that, e to the 2x, sine x, subtract integral of v du dx, so 2 e to the 2x, sine x, dx. I hate it when I can't quite fit it all in. Yeah. Maybe just get rid of that there for the moment, shall we? So let's just tidy this up a bit. E to the 2x cosh x, subtract 2 e to the 2x sine x, and then plus, and then let's just take that 4 outside the integral bracket, 4 e to the 2x sine x dx. Yeah, I can fit it all in. Okay. Now, where to go from here? Some of you might be thinking, hang on, you're kind of going around in circles, aren't you? Because this integral is the same as the one we started with. So how are we going to do that? Yes, you're right, and I'm hoping that you've seen this maybe once or twice before in the standard A-level course. If you haven't, this is an excellent opportunity to remind you of a wonderful technique that I really love in integration. Okay, yes, that is exactly the same as that. Okay, but notice I've called this integral I, haven't I? I've said this integral is I. Yep. So in other words, I've got I. That integral is equal to this, and this integral I is equal to that. This here is 4 times that original integral, so 4i. So what I'm going to do is, purely so I can write all this on the same board, I'm going to rub this line off, okay, and I'm going to write down e to the 2x cosh x, subtract 2e to the 2x sine x plus 4, and then instead of that integral I'm going to write I. Okay, happy with that? Yeah. I'm so glad you said yes. Okay. And what I'm going to do is I'm just going to rearrange it and make I the subject. Okay, so I'm going to bring that I to that side, so I have 3i, and then I have to bring all of this onto that side, won't I? So 2e to the 2x sine x, subtract e to the 2x cosh x. Okay, and then divide everything by 3. I'm going to get the integral is, just write that better as 2/3 e to the 2x sine x minus 1/3, oh squeeze that in, e to the 2x cosh x, and once all the integration has been done, just don't forget the plus c, okay? So, that is what I'm going to get, alright? But hang on, you might now think, well, that is completely different from the answer that we had before. Look how nice and simple that was. Well, the next thing will be to see if we can just rewrite that in terms of exponentials. So let's give that a go. Okay, so writing this in terms of exponentials. So we've got, I'll tell you what, I'm going to write it a bit further to the left to try and squeeze it all in. So you've got 2/3, and then e to the 2x, and then that's going to be a half, so let's just write that as 1/3. Okay, e to the x, subtract e to the negative x. Okay, and then this will be subtract 1/3 e to the 2x, and then that would be a half, so let's write that as 1/6. And then e to the x plus e to the negative x. Don't forget the plus c. And let's just see if we can simplify this a little bit. So it will be 1/3 e to the 3x, subtract 1/3 e to the x, and then subtract 1/6 e to the 3x, and then subtract 1/6 e to the x, plus c. 1/3 is the same as 2/6, isn't it? So I'm going to write 2/6 there and there. So 2/6 e to the 3x, subtract 1/6 e to the 3x is 1/6 e to the 3x. And then you've got negative 2/6 e to the x, subtract 1/6, so that's negative 3/6, so So it's negative a half e to the x plus c. What was on our answer board? Oh my word, just look at that. Isn't that fantastic? One of the many reasons why I love integration, okay? When it comes out nicely like that, it's just like, yay, done, okay? Yeah, sorry for me getting over-enthused, but it is nice, okay? Yeah, so look, I know I did a lot of rubbing off and and rewriting and so on. Yes, this is a much longer method, but yeah, by parts does also work as well. But yeah, of course, the method I showed you earlier is, but isn't it nice when you can see a technique like that and you get exactly the same answer, okay? I'm just going to leave you with this whole idea of the I and the 4i. Remember that, because it does make a reappearance later on in our integration unit, okay? I really hope you enjoy the integral. You still loving the integral? Yeah, I am, okay? I just want to do a little bit more on this, okay? So interestingly, if you're using the same textbook as I am, the textbook suggests that if you were to do integration by parts on this, shine 2x there, then the whole thing breaks down. That's a rather interesting comment to make, isn't it? Okay? I'm not happy with that unless I actually see it happen, okay? Same should be with you as well. If a textbook just makes a statement like that, it breaks down if, you kind of want to know why. So should we just go ahead and do that? Yeah, let's go ahead and do that. Okay. So e to the 2x, shine 2x. Let's just see why this is going to break down. Okay. Now I've just kept my work in there because I'm just going to change various bits to try and make it fit. So we started off with the by parts, of course, u and du dx. So back to dv dx. That will be shine 2x for this one, and then the integral of that will be a half cosh 2x. Okay. Now let's see how we change this. So the uv is going to be half e to the 2x cosh 2x. So let's just put in a half there. Okay. And then subtract u dv dx. Sorry, v du dx is going to be a half times that. So in fact, you just went at the 2 there. Okay. You'll have e to the 2x. And it'd be cosh 2x. Okay, seems to be fine so far. And then what? So we had a half e to the 2x cosh x. Okay, that's fine. This one here, we then did by parts again, didn't we? Okay, so what I'm going to do is I'm going to change that again. So this time that's going to be what? Using the right colours here, cosh 2x, and then that will be again, well, I say again, similar, half shine 2x, won't it? So what have we got here? So when we let's just get rid of this line here. Okay. So when we integrate this, we're going to have it was in brackets, wasn't it? uv. So half e to the 2x shine 2x, and then subtract the integral of v du dx. So half times 2 is 1. So e to the 2x shine 2x dx. Okay. Now what I'm going to do is I'm just going to get rid of all this. Okay. Because I'm going to need some space, and we'll just follow it through. Doesn't seem to be breaking down so far, does it? So let's just see what's going to happen. So we've got half e to the 2x cosh x subtract a half e to the 2x shine 2x, and then that'll be plus, well, it's integral of e to the 2x shine 2x dx, yeah? Which is that? Which is just I, yeah? So that's the same as 1/2 e to the 2x cosh x minus a half e to the 2x shine 2x plus I. And then what are we going to do? Oh, I is equal to this. Oh dear, that doesn't look quite right, does it? So what we're essentially saying is that these are going to cancel, and you're going to have 0 is equal to that. Yeah, hence that's why it breaks down. Okay, but I thought you might like to actually see that process for yourself, okay, to understand that. Okay, so what the textbook is saying is when you've got e to the say alpha x shine alpha x, then the by parts is actually going to fall down for you. It's not going to work for you. Just to reiterate, your standard approach is put it in terms of exponentials. As lovely as all this work is, we still want the simplest possible way, don't we? Okay. I'm hoping you found that useful and interesting. Okay, here's an example of something that is relatively straightforward to write down, but it's actually quite a thinker, really. Integral of sec x dx. Come on, pause the video, have a think about it. Bit of a head scratcher, that one, isn't it? Okay, but this is why I like integration. Took me about 10 seconds to write down, but it is one that you have to think about. Now, the great thing about hyperbolic functions, as a reminder, is you can write them in terms of exponential functions. So we can't find an identity that's going to help us with that, really. So let's just do the next obvious thing, write it in terms of exponentials. So remember that cosh x is the same as e to the x plus e to the negative x all over 2. So this one we can write as the integral of the reciprocal of that, 2 over e to the x plus e to the negative x dx. Okay. Now, even then, you might think, well, what's the next step? Well, what we could do is just make it a little bit simpler. And what I mean by that is, notice you've got e to the power of negative x there. A common technique is to multiply top and bottom by e to the x, so all the powers are positive. So we'll do that. So we'll have integral of 2 e to the x over, and then the bottom will be e to the 2x plus 1 dx. Okay. Now, what to do next? This is where I'm going to remind you about the method of substitution. Yes, substitution. You're thinking, when is that going to come back? Right now. So I've gone through by parts with you again. Now we're going to use substitution. Okay, let's just do this. So you need to make a substitution to try and make this work. So let u equal what? Well, we're going to make u equal e to the x. Why have I decided to make u equal e to the x? It's because we could then simply write e to the 2x as u squared. If you think about it, if we made the substitution let u equal e to the 2x plus 1, it's not going to work out for us. Give it a go if you want, but it's not going to work out. Letting u equal e to the x is the way forward. And then du dx is also e to the x, and then dx is going to be du over e to the x. So let's just substitute this in and see what we get. So 2 e to the x, so it's going to be 2u all over, I said that would be u squared, didn't I? Plus 1, and then dx is du over e to the x, which is u. And notice how the u's cancel out. That happens with substitution, doesn't it? The idea is that the method makes the integral much simpler for us to deal with. So I'm just going to cancel those now, and then that's our integral. 2 over u squared plus 1. Now that is one of your standard integral results that you need to be looking for. Okay, what is the integral result? Integral 1 over x squared plus 1. It's arctan x plus c. Okay, so this is going to be 2 arctan u plus c. Okay, if you don't believe me, just look up the standard integral results. Okay, you need to be able to know and use them. And so our answer is going to be 2 arctan, and u is e to the x plus c. Okay. And then we're done. I'm not quite done with you yet, no. I just want to come back to that integral once more, okay? So let's just compare it with the integral of sec x. Again, something that was actually pretty difficult in the standard A-level course. Here's a reminder, okay? The integral of sec x is the natural log of sec x plus tan x plus c. And the reason that works can be explained as follows, okay? If you start off with y equals the natural log of sec x plus tan x, then you can differentiate it, and you get this, okay? So obviously differentiate the natural log, you get 1 over sec x plus tan x, and then using the chain rule, differentiate the brackets, that would be sec x tan x, and that would be sec squared x. So that goes on the numerator there, like that. Then you can factorise the top as sec x multiplied by tan x plus sec x, and then notice these bits on the top and bottom will cancel, you're just left with sec x. Okay, this is what we're looking for, okay? Remember that? Well, not surprising if you don't, because it's one of the more difficult integrals, okay? So let's compare that with sec x. Can a similar approach be used? Maybe pause the video and just try and find out. Having trouble getting started? Well, let's just say we're looking for a similar result, okay? Let's just suppose we begin with y equals the natural log of sec x plus tan x, okay? And then just find what you get when you differentiate that. That's what you're trying to do. Maybe pause the video now and work through it and see what happens. So when we differentiate that, let's just write out. So first of all, on the denominator, you'll have sec x plus tan x, okay? And then on the numerator, when you differentiate the brackets, differentiate sec x, you'll have negative sec x tan x, and then differentiate tan x, you'll have positive sec squared x, and then you can factorise again using sec x, so sec x, and then let's just write it this way around, because of the negative, you have sec x minus tan x all over sec x plus tan x. Now can you see these two are different, so they're not going to cancel anymore, are they? So that is why this technique is not going to apply, and that's why our solution is not going to be similar to the trigonometric counterpart, okay? Anyway, it's more for the reminder actually of how to integrate sec x, okay? But I thought I'd just slip in why you can't use a similar approach for sec x, okay? Just remember, with hyperbolic, a lot of the time, putting it in terms of the exponentials is normally the way to go. Well, that's the end of this video. It might have been a long one, but there's a lot of important integral techniques that I'm hoping that you've picked up on, okay? Remember, practice as many questions as possible, okay? I cannot say this too many times. Keep on practicing, okay? It's the only way to be, a master of integration, okay? I'll see you again.